All right, hello everybody. Thanks for being here today. My name is Jondall Norris, and my project for the summer was a deep learning approach for the reconstruction of the Great Lakes ice cover spatial distribution. And I was mentored by Hazem Abdelhady, David Cannon, Ayumi Fujisaki-Manome, and Dani Jones from CIGLR, and James Kessler from NOAA GLERL. All right, a little bit about me. I recently got my BA in physics from Bowdoin College in Maine. I'm from Portland, Maine. I also studied a lot of oceanography, and I did some work on polar oceanography and ice geophysics at UNIS, which is in Norway. My academic interests include physical oceanography, limnology, polar science. I love studying ice and doing modeling and looking at climate and weather as well. And some of my non-academic interests include cold places. Here are some pictures of me in some cold places, including Lake Superior. All right, so getting into this project. So thanks to the prior work of my mentors and previous summer fellows, we have some really great data sets that we can use for an effort like this, namely daily satellite-derived maps of ice concentration between 1972 and now, and daily air temperatures at 24 locations along the coast of the Great Lakes between 1897 and 2023. Also, Hazem has previously used a deep learning model to predict ice on Lake Michigan using ERA5 reanalysis data. So we have some precedent that this type of model works for ice modeling. And so our big question is here, can we predict Great Lakes ice cover spatially beyond just the lake-wide scale and temporally beyond the annual scale from these scattered historical air temperatures using deep learning? And this kind of gets at this bigger question of what are the long-term changes in Great Lakes ice cover? So before we get into the specifics of the model, let's talk a little bit about deep learning. You've probably heard a little bit about machine learning already today, and I'm going to throw my hat in the ring at trying to explain it too. So because we have some input data and some examples of the outputs we want our model to learn how to reproduce, this task falls under a family of techniques called supervised machine learning. I also noticed that, sorry, some of these borders are going to be really big. I think there was some issue transferring my presentation over, so sorry if some stuff is covered up. At the simplest level, supervised machine learning is just a linear regression model. You're probably all familiar with this, y equals mx plus b. We can also have multiple linear regression, where we have multiple inputs, each with their own parameters or coefficients associated with them, to predict one output. And at this point, we can kind of begin to think of this model instead of as an equation, more conceptually as a neural network, where we have a bunch of nodes of information in an input layer, kind of like at the bottom here, which all connect to form a single node in the output layer, which is our prediction. And finally, we can add complexity to this basic neural network by inserting additional layers with multiple nodes of information, where each node is, again, this linear combination of all the nodes in the previous layer. And so this adds depth to the network, and that's where the deep in deep learning comes from. And with some additional steps, this allows these models to represent more complex nonlinear relationships than we can with just linear regression. I also ended up using a couple other types of neural networks as well. Recurrent neural networks, like you heard from Matt, are similar to deep neural networks, except they consider info from current and previous time steps, much like other time series models. They're really good at learning from temporally coherent time series data, and I use that same type of RNN that Matt talked about called long short-term memory. I also use some convolutional neural networks in my model, and these calculate nodes between layers by only considering the current and neighboring cells in the previous layer instead of all those nodes. And they use only the same few parameters between each layer, or convolution, which makes them very computationally efficient and really good for working with gridded or spatially coherent data like images or maps. So the larger and more complex we allow a model to get, the more hyperparameters or options you have to specify, and the more possible overall designs or architectures are possible. much like when you buy a really fancy car with all the specs and you got to like decide what type of seats you get, or like you go to the ice cream store that has like all the different toppings and you can't really know which one is going to be best, what combination is going to work for you until you try it. And that was about 80% of my summer, was just trying all these different combinations. And so I kind of worked my way up from the most simple models with only a few layers to much more complex ones with a bunch of layers that incorporate different techniques by kind of testing some ranges of options and settings for each model, training and running the models in the UMich HPC, and then checking to see what worked best and kind of moving on to the next model. There were a few reoccurring challenges that guided my development process. So first of all, this kind of overall task is a little bit unconventional. And so this is like, how do we get 2D gridded outputs over a lake, this is ice concentration, from several non-uniform land-based inputs, air temperatures? Secondly, how can we make our model learn the underlying physical processes that govern ice formation and not just overfit our training data, which kind of became, how do I incorporate my 1D inputs, the air temperatures, with some 2D gridded inputs like depth and shoreline proximity that can help the model learn these physical processes? And finally, how can I incorporate both spatial and temporal learning into one coherent model? So with that in mind, my final model uses kind of this two-phase design where the model first treats inputs temporally and then spatially. The model was designed for Lake Michigan and developed just on Lake Michigan, but it's extended to the other 4 lakes where each lake is treated separately. The model uses the daily average temperatures from that data set I mentioned before at all 24 of those stations, and 4 trailing averages as inputs. Again, 4 trailing averages at each station as inputs, and also incorporates depth, shoreline proximity, latitude, and longitude in that second spatial phase. The outputs are daily ice concentrations at 18-kilometer resolution. If we look at this figure on the right here, the model is trained on ice charts between 1972 and 2010, and validated using charts between 2010 and 2023. Because of inconsistent starting dates and ending dates of the ice charts, dates between November 1st and May 31st were filled with 0 ice days. And due to missing data in the temperature data set, about 3% of all days over the hindcast period and the training and testing period were not included. So this is kind of what the architecture of my final model looks like. Here we have this first spatial phase, this first temporal phase. So the time series at each station and those moving averages pass through some long short-term memory layers. And so again, this is a temporal time series processing. And then these fully connected layers are used to scale the LSTM units up to the number of lake cells in our output grid. In the second phase, the output of the fully connected layers is projected onto the lake cells on an empty grid. That is the same grid as our output, while the land cells remain zeros. Then this grid is joined with our spatial inputs, again, latitude, longitude, depth, shoreline proximity. It's joined with those and then passed through those spatial convolutional layers. And from there, we get our outputs. So I assessed model performance on a local cell-by-cell basis as well as on a lake-wide average basis. Comparing local predictions to ice charts over the validation period, root mean squared error averaged across all cells ranged from 14.4% in Lake Superior to 10.4% and 8.3% in Lake Michigan and Lake Ontario. And note that these are absolute units of root mean squared error because ice concentration is in percents. Comparing lake-wide averages, RMSE ranged from 3.6 for Lake Michigan to 7.2% for Lake Erie. We suspect Lake Michigan performs well here because it has, well, because I developed the model for it, kind of, maybe, but also because it has the most coverage by those air temperature stations. Performance was worse along the coast and in small bays and inlets where we typically had more ice. And then bias across each lake was typically spatially coherent, especially after we started using these convolutional layers. with certain sections of the lakes, for example, Eastern Superior, the Northern Channel, most of Lake Erie having an average negative bias, while others like offshore Lake Michigan, offshore Lake Huron, and Western Lake Superior had an average positive bias. Comparing our lake-wide average predictions to physical model output from the Great Lakes Coastal Forecast System, we see some mixed results. For example, in Lake Superior in 2019, my model in blue performed quite a bit better against these predictions in black compared to GLOF's in orange. However, on the same year in Lake Erie, my model underestimated pretty hard while GLOF's did a much better job. But in general, both performed really well in Lake Michigan over the years I checked. And over this 2018 to 2023 period that I got GLOF's data for, my model was within 1% or better than GLOF's in terms of lake-wide RMSE across all lakes. So our big result here is these hindcasts, basically. So these are predictions. These are daily maps from fall of 1897 to spring of 2023 at 18 kilometer cell size across all 5 lakes, with the exception of those missing days I mentioned before, which is give or take about 3%. These predictions more than double our current observational record, adding 75 years to our current 53 years of ice charts, albeit at about 1/10 the spatial resolution. And so with these results, we can interrogate not just what each lake looked like each year, but what specific regions might have looked like on specific days in the past. I haven't had these results for that long, so I haven't done that much analysis, but kind of just fitting a basic linear trend to the annually averaged ice cover, I found that the strongest regional trends of ice loss are kind of in these more offshore open areas that typically experience a lot of ice in them that they can lose in Lake Michigan, Lake Huron, and especially Lake Superior. Smaller bays, while they usually have a lot of ice cover every year, they do not appear to be in decline as fast as some other high ice regions. But again, I haven't really been able to look at this too much, but I'm sure there's a lot more that you could pull out of these trends with more time. On a lake-wide basis, trends since 1897, shown in red here, are all negative, but pretty small, less than 1% loss of annual average ice cover per decade. However, trends since 1975 have accelerated by a factor of 3 to 8 times across all lakes, which is similar to some of David's recent findings as well. So as a physics guy, you know, I was not a machine learning person until the start of this summer. I have some trouble trusting models like this. And so kind of over the past few weeks, I went looking for some ways to verify these results. And while there aren't any more ice charts, that we can create metrics like RMSE with for these past years, there are sparse observational records dating back to well before the hindcast began. And so to demonstrate, I wanted to look at the 1903-1904 ice season, which my model predicted was a pretty big year if we look at all these peaks in annual average ice cover. And so I wanted to look back and see if I could find any evidence that this was as big a year as my model suggests, and see if I can confirm any of my results. So sure enough, again, sorry these borders are like huge. Sure enough, I found a bunch of newspapers with some really good descriptions of ice and some really funny headlines as well. And they all confirmed that indeed this was a really unusual year, you know, like ice 40 feet thick, like Milwaukee Harbor had to close for the first time in 10 years. Like very unusual, ice without end, bergs more than 100 feet high. So this was definitely a big year, and people back then definitely recognized it. And we can dig in a little further too. So one weekend in December of 1903, Captain Persons of Alpena had a really rough trip trying to get back and forth from Thunder Bay Island, which is right off of North Point in Alpena. And while there isn't much ice in Lake Huron at this point, we do see a little bit of ice forming along the coast between North Point and Thunder Bay Island. So maybe a little bit less than Captain Persons reports, but it is indeed unusual to see the coast starting to freeze around this time of year if we compare to the same day averaged over the 6 years prior and 6 years following. Later, in February, the True Northerner reports massive icebergs in Muskegon and lake ice extending out to the middle of Lake Michigan from each shore. And sure enough, our model shows only a few open water cells in the middle of Lake Michigan. And again, almost no ice at that same day in the years before and after. Finally, in March, a Weather Bureau report, and this was back when they were under the USDA and NOAA did not exist for another 60 plus years, describes no open water except on the west coast of Lake Michigan and no open water in Lake Erie between Cleveland and Buffalo. And sure enough, this is pretty much exactly what we see. This arrow should be a lot smaller, sorry guys. But as you can see, there's no ice between Cleveland and Buffalo. Or sorry, no open water. And so in conclusion, through this modeling effort, we produced predictions of Great Lakes ice concentrations between 1897 and 1972 at an unprecedented temporal and spatial resolution that will hopefully be available soon. And these long-term records can really contextualize our current or more recent trends that we see in ice cover and help us predict what the future of ice might look like in the Great Lakes. But most importantly for me, I think I've learned this summer that ice really matters a lot for so many physical and biological processes in the lake, and it's really important to the people who live here too. So I hope that these predictions can help you all answer questions that you have in your own research about what has happened in the Great Lakes in winters past. I want to give a huge thank you to Hazem and the rest of my wonderful mentor team, to Mary and Margaret for supporting us this summer, to my undergrad advisor, Colin Resler, for recommending me to this position, and everyone at CIGLR and GLERL for being so generous with your time and expertise and welcoming us into your work during this really challenging time. So thank you all.
Great job, Jondall. Questions?
This is not pure deep learning model. It's a combined thermodynamic and deep learning model. Is that correct?
No, there's no physics in this model.
You use the temperature. Use a temperature.
The temperature is the input, so you could call it purely thermodynamics in the sense that it doesn't have any. There's no wind. There's none of that sort of physics. But I personally I don't think it's thermodynamics because it's like zero physics. It's all like the internals are all regression, right?
Okay.
Yeah.
Okay. Thank you.
Very great presentation. I really, as someone who knows almost nothing about ice or modeling, really appreciate that piece you did at the end, looking at how your model could be verified by some of these old news reports. That was really cool. It's not something I've seen done maybe ever. So I just wanted to say kudos because I really appreciate that.
Yeah, thanks.
Yeah, I agree with that comment, Rochelle. How were you able to find those old news articles?
I kind of just like Googled old Michigan newspapers.
Okay.
And there's I think it's the Central Michigan University. That's a school, right? Yeah.
Yeah.
Central Michigan University Library has a really fantastic online archive of historical local newspapers from Michigan. So I was able to, and they'll like do OCR, character recognition, on all of them, and it's generally pretty bad. So I basically just searched like 1903, 1904 ice, and then just went through a bunch of different newspapers, and about like 80% of them were ads for ice cream stores. And a lot of them were also like typos and stuff, but it did find a lot of these headlines and people talking about ice. And so I was able to kind of just like sort through those and find some that had some cool stories.
Sounds like a really, really cool resource we might want to look into. I was imagining you in the library looking through all the microfiche.
Yeah.
Hey, yeah, great talk and great work this summer. I wanted to point something that I hadn't noticed before in our meetings. The model seems to be struggling most when the ice is like locked in. So when it's like land fast. So you pointed out those 2 bays in Lake Superior, and then you pointed out like a super high ice year in Lake Erie that it wasn't capturing well.
Like on Gloffs.
Yeah,
Yeah.
as compared to Gloss. So I think, I don't know, I'm wondering if there's a way for us to add an additional kind of like, to Gia's point, we kind of fake the physics with some of this stuff.
Totally.
Like we're feeding it like a long-term integrated temperature and some other things to get at the points that we want to get at.
Mm-hmm.
And I'm wondering if we could do that with kind of like when the ice is stuck to the shoreline. Do you have any ideas for that? I know this is very random.
No, I mean, in times when I've like just kind of spot checked, like okay, how do we look, especially within like when I have the ice charts, you can kind of see how it doesn't know that, because it's always, when you have like the ice edge is like being pushed around in the lake, it tends to be like a very sharp boundary before it's like super broken up. Or like if you have like that, basically that year in Lake Michigan that I showed, it probably, in reality, it was probably more like that sharp ice edge had been pushed out off the western coast, and then there's open water there. But as you can see in my model, it was this smooth transition. And that's kind of the same thing you see everywhere, is like it kind of just prefers to smooth, and it doesn't realize that it's, again, that sharp edge and that it's these flows being pushed around. There's definitely more tweaking you could do to try and represent those processes better. And I think there's also like a bunch of different types of modeling in this realm, and like different functions that perform better than just like the regression functions that I'm using. So it's definitely possible, but nothing that I like had off the top of my head or I was imagining about trying to fix that.
Okay, thank you so much, Jondall.
Thanks.